Good morning, everybody. We're going to get started here. I pulled a few questions from the homework to go over to help you out a little bit with that Chapter 9, Mastering Chemistry. So we'll start with that, and then we'll move into Chapter 10. So I saw questions on this one, and I can look and see at the homework of the people who started the homework and, how many people were struggling with the question. So how many people got it right, and, kind of a gauge of difficulty based on how many people requested answers, how many times it took people to enter an answer before they got it right. So I try to pay attention to those things, and I picked some of the questions that it seemed y'all were struggling with the most. So let's start with this one. Assuming constant conditions, how many milliliters of oxygen gas react to give 2 liters of this compound? So dichlorine trioxide. You see that there's a chemical reaction here. But what did we say about stoichiometry? We have to have a balanced chemical equation. This equation is not balanced. So if we look at our reactant side, there are 2 chlorines and 2 oxygens. On the product side, 2 chlorines, 3 oxygens. That's a problem. So we have to balance this first. So I'll give you a couple of minutes. I want you to balance this equation. And then I'll jump back in, balance it, and solve. So if you feel comfortable to keep going now that you know, oh, I got to balance it first, then that's fine. Go for the gold. Otherwise, wait for me. Okay, I'm going to start balancing, and then we'll do the problem. So clearly there's a problem with the oxygen. It's not balanced. Lowest common denominator here is 6. So multiply by 2 on the product side and by 3 on the reactant side. We haven't touched the chlorine on the reactant side, but we're putting a 3 in front of here, a 2 in front of here. So we've got 6. 3 times 2 equals 6 oxygens. And then on the product side, we now have 2 times 2 equals 4 chlorines, and 2 times 3 equals 6 oxygens. Now I've got to balance the chlorine. The lowest common denominator here is 4. We're going to multiply by 2 on the reactant side. And let's do a final check to make sure that we're really balanced. We've got 4 chlorines and 6 oxygens on the reactant side. And we've got 4 and 6 on the product side. Now we're balanced. Now let's look at the problem again and see what we actually have to do. How many milliliters of oxygen gas react to give 2 liters of dichlorine trioxide? What we're given is a volume. and we're asked how many milliliters of oxygen gas, which is another volume. That makes this a volume-to-volume stoichiometry problem. I have to use the balanced chemical equation to write a mole ratio. But with volume to volume, we don't have to just say moles, we can actually say liters. So this is really the only hard part of the problem. What we're interested in is the oxygen gas and the product. We put oxygen gas at the top, product at the bottom. That way it will cancel. But we have to do one more thing here. The question is asking for milliliters of oxygen, not liters. So we have to convert our answer to milliliters. So when you do that math, you should get 3,000 milliliters. Now, for sig figs, we've got 3 sig figs in our given information, but our number, the way that we've written it, currently only has 1. So we have to write this in scientific notation to get 3 sig figs. So there are a couple of points here that you want to remember. 1, balance the equation. I think that was probably the biggest problem for you all, is that you didn't realize these equations were not balanced. And I gave you the warning, but I think we forgot. You don't always get a balanced equation. We practice with balanced equations, but an unbalanced equation is fair game. The second thing is units. Check for the proper units in your final answer. So if it's asking for milliliters, you give milliliters. If it's grams, you give grams. If it's milligrams, you give milligrams. You have to pay attention to what the question is asking. Are there questions on this one? Let me know if this helped to clarify some things for you if you were struggling with this problem. I know there are others like it. Okay. I know there are other questions like this, where you're asked for the number of milliliters, you have to balance an equation, that kind of thing. So we're not going through all the homework problems. I just chose about 3 problems that should help cover all the problem areas that y'all had. So let's move on to the next one. We have a reaction. This is a combustion reaction. Oh, for like a volume to volume? No, I'll use liters or milliliters. The only time where I would do that on an exam is if it's open note. Then I would, maybe I could say something else, but I would give you the heads up like, hey, by the way, here's a hint. This is the unit. It's not liters. So you need to convert. Yeah, I'm not trying to trick anybody on an exam. Exams are worth way too much. So how many moles of butane gas react to produce 2 moles of water? This again is an unbalanced equation. We have to balance it. And this one is a little bit trickier to balance just because, so we didn't cover combustion reactions in class per se, but we did talk about how to balance equations. And with this one, to balance it, you'll have a fraction, which you need to get rid of. I'll show you what I mean. I'm not going to give you anything this evil on the exam, but this is a good challenge question, particularly if you have to take 106 after this. When you balance this equation, this is what you end up with if you don't do any multiplication to get rid of that fraction. With combustion reactions, it's common for you to have to start by writing a fraction for the oxygen gas and then multiply through to get rid of it. Since this is not a question about balancing an equation and writing that properly, we can actually just leave it the way it is. So if you were struggling on this one, I would encourage you to write down this equation so that you can do the problem. From here, it's just a simple mole to mole question. We are asked about how many moles of butane we need to react to make 2 moles of water. I do not teach 106. I teach 103, I teach 104, and I teach biochemistry. I'm sorry. I know. Yeah, I'm a biochemist. So I teach biochem. So if you are animal science or pre-med and you don't want to take the 400 level biochem course, then you'll see me again. Although I didn't teach it in the fall, but I think I'm scheduled to teach it this fall. I'm sorry. I know. Yeah. So I do biochem and biochem labs. I don't do the gen chem. So what I'll do is I'm going to go through. If you would like a chance to kind of redo some problems because you were struggling that much, send me a course message. You got to send it to me, we'll say by 5 o'clock today, and I'll remind you guys at the end of class too. And I will reset the questions that you would like for me to reset, because I want to give everybody a fair chance. So if you've already completed the homework and you're like, I could get a better score, let me know. But you have to tell me which problems you want me to reset, and I'll do that for you. All right. So we need to make 2 moles of water. We've got to figure out how much butane we actually need for that. We go to a balanced equation. Yes, I'll do it for both. You're welcome. So when you message me, just specify which one's for the homework and which one's for the quiz. And I need it by 5, so it'll give me time to do it. Y'all know I got other stuff to do. So let me know by 5 so I can work on it tonight. Make sure everybody has their clean slate for those problems. And then you have until Sunday to get it finished. From the balanced chemical equation, we've got 1 mole of butane for every 5 moles of water. So when you divide 2 by 5, you get 0.4 moles of of butane. I don't want anybody getting confused if they look at the notes and see unbalanced, because that one is balanced now. Questions? Okay. So here's the last one that we're going to do. And it's more of the same in terms of making sure that the equation is balanced. We're starting with 10 liters of hydrogen chloride gas and 43.5 liters of oxygen gas. And we want to know what volume of chlorine gas is produced. And we're told to assume that all gases are at the same temperature and pressure. What that means is that we can say liters instead of moles when we have a balanced equation. The other trick to this one is recognizing what kind of problem you have. We're starting off with volumes, and we're asked about what the volume of chlorine gas is. So it's a volume to volume. But we have 2 amounts that we're starting with. 10 liters of hydrogen chloride gas, 43.5 liters of oxygen gas. So this is also a limiting reagent question. I use reagent and reactant interchangeably. So we have to do 2 mini problems so that we can figure out how much chlorine gas we make. So first things first, let's balance the equation. So clearly, we've got some work to do. We'll start with the oxygen because this one's the most complex. It's O2, and then we see it in water. There's only one. So let's start there. Now let's see where that takes us after we do some multiplying. So we balanced out the oxygen, but now we've got a bigger problem with the hydrogen and the same problem with the chlorine. Since they're in the same molecule on the reactant side, we should be able to solve this by using the same lowest common denominator. So let's see what happens. We've got 4 hydrogens on the product side. So we've got to multiply by 4. So almost there. Now we should be balanced. So that one was a little bit more involved, but that's the balanced equation. Now we can do 2 volume to volume questions to figure out how much chlorine gas we make. The first problem that we're going to do is going to be if we have our HCl, how much chlorine gas do we make? We go to our balanced equation and we write out that ratio. On top, we're going to have the amount of chlorine. On the bottom, we're going to have the number of moles, or liters rather, of HCl. So in your calculator, you're doing 10 times 2 divided by 4. So that's 20 divided by 4, which gives you 5. The second problem that we have to do is if we had all this oxygen, 43.5 liters of it, how many liters of chlorine gas would we make? Again, we use the balanced equation. We put the chlorine in the top and the oxygen in the bottom. So in your calculator, you take 43.5, you multiply by 2, now we have to choose which one makes the least amount of product. That would be up here. So the volume that you would make is 5 liters because it's the smallest of the two. Questions here? Hopefully this was helpful. Yeah, no problem. If everybody's struggling, I'm not going to be like, well, I guess you all just struggle then. Everyone's going to fail. Like, that's not that's not okay. The point of this whole thing is for you to understand it and do it with confidence. So if you don't feel that you can, some of that work is on you to do and make sure that you are diligent, but it's also on me to make sure that I provide the tools that you need and the references that you need. So if you feel like, man, I'm really struggling, I'm glad so many people reached out. So that makes me feel good that you felt confident that you were like, she's going to do something about this. Because you're right, I am. So again, if you need me to reset some of your questions, if you're like, man, I lost a lot of points on some that I now understand better, send me a message using course messages by 5 o'clock today, and I will help you out. So that's it for the Chapter 9 help. Those 3 problems really covered what seemed to be the gamut of problems that folks were having. Units, so answering in the right units. And don't forget sig figs. And making sure that you balance the equation. And the combustion problem is usually a little bit of a trickier one for folks to do. So with that, we're going to head into gases. Totally different topic. A little bit easier. There's still math, but the math is not as bad. I think Chapter 9 is probably the hardest chapter for folks. So Chapter 10 is a little bit of a breath of fresh air. There is a video already on YouTube that goes through all the concepts and stuff. So I'm not going to spend as much time on that. I'll address things and try to point out, okay, you should know this, you should understand that, but I'm not going to go through and reteach that. Make sure that you watch the video, because you will not get the full experience if you don't. So for example, the 5 properties of gases, we talked about them in Chapter 3, which was a long time ago. They're back. You need to understand these and know these, kind of what they mean. I'm not going to walk through these and go over them again. I do that in the video. But make a note to yourself, if you haven't watched the video already, that you should know these and understand what they mean. I'll kind of pause on here for a second if you're trying to jot something down, but it's already in the notes for the pre-recorded video, and it will be in the notes for the live lecture. So you don't have to write down everything on here because you can just look at it again on your computer or your phone. Technology's great. I will talk a little bit about what gas pressure is, just to make sure that we're all on the same page, because we're going to be talking about pressure amongst other things for the rest of this class. So gas pressure results from all the gas molecules in a container striking the walls. That's literally it. And that sounds kind of crazy because you can't even see these gas molecules. But remember, there's so many of them, and they're all moving so fast. They've got a lot of kinetic energy, which means they can hit the walls of a container collectively with a lot of force. And at a higher temperature, you've got gas molecules moving more quickly and striking the walls more often and with greater force. So that's going to increase the pressure on that container. Atmospheric pressure is what we experience every day. And it's simply a result of all the air molecules in our environment pressing down on us and everything else on the surface of the earth. The barometer was invented to measure atmospheric pressure, and a picture of it is on the right. I talked about how the barometer works in the video, but I'll briefly go over it here. You've got an open container of mercury, and it's got an inverted glass tube. Mercury is a super dense metal liquid. And when the pressure from the atmosphere pushes down on the mercury, it causes some of that mercury to travel up this tube. You can literally take a meter stick and measure how high the level is. You can also take a ruler or yardstick or something like that. And whatever you measure, that is the atmospheric pressure. So notice in parentheses it says 760 millimeters. That's 760 millimeters of mercury, which is one of the ways that we can measure pressure. The other way that's shown is 29.9 inches of mercury. And all of those things are equal to 1 atmosphere, ATM. So because I just showed you 3 different ways that you can represent pressure, best believe there's going to be some pressure conversions here. And I'm going to show you that. So this table, do not memorize it, but it will be helpful for you for homework and for the quiz for Chapter 10. The ones that I will be testing you on mostly: atmospheres, millimeters of mercury. You might see torr thrown in there. Those are the ones that you'll see most often when you're dealing with chemistry. If you're doing physics, you might see PSI, which is pounds per square inch, or kilopascal, or pascals. Don't really deal with that in chemistry the same way. Those are really physics related. But again, don't memorize this. I will give you the information in this chart that's relevant to the questions. The other thing I want to point out is that the ones that I've put a star next to, they have this exactly next to them. What that means is that it's an exact number. And exact numbers do not count for sig figs. So when you're doing pressure conversions and you're converting, say, atmospheres to millimeters of mercury, the 1 and the 760, they're exact. So you don't use them when you're determining how many significant figures your answer should have. Any questions so far? Okay. Then we're going to do, so I've got some sample problems in here. And what we'll do is this week, I don't have like multiples of each problem type. We're going to go through. If you feel confident to do it on your own, you do it on your own. If not, you can watch me do it. No big deal. Next week, we'll have a little bit more kind of hands-on with some of the gas laws and things that we cover this week. And then we'll do a similar thing where I go through some different sample problems for you that you can feel free to kind of go ahead on your own and do. So here, we just have a standard pressure conversion. Barometric pressure is 755 millimeters of mercury. What's the pressure in atmospheres? So what you need to know for this one, which you'll be given in the exam, is that 1 atmosphere is equal to 760 millimeters of mercury. And if you're saying to yourself, man, that looks a lot like what are those things called? A unit equation. It is. It's a definition, right? And if we have a unit equation, then we can write unit factors. So let's label this. The unit factors that we can write from this: 1 atmosphere over 760 millimeters of mercury, and the reciprocal. Those are the unit factors. Starting with 755 millimeters of mercury, which one of these unit factors should I use to convert from millimeters of mercury to atmospheres? We should use A. So we know that our answer is going to be in atmospheres. All we have to do is divide 755 divided by 760. How many significant figures should we have in our answer? Yes, we should have 3 sig figs in our answer. And that's our final answer, 0.993 atmospheres. You'll see 1 or 2 problems like this. It may be in a larger problem, in terms of the final because we don't have a chapter 9 and 10 exam per se. So I'll try to give you a heads up along the way how you might see some of these things incorporated into the final. So let's keep going with gases. There's 3 variables that affect the pressure. There's the volume of the container, the temperature of the gas, and the number of molecules. The volume of the container we'll call V, and the relationship here is indirect. I go into more detail for these 3 in the video, and we're going to cover these kind of with the gas laws that we're going to cover. So I'm not going to go too much into detail, except to give you some of the terminology. There's an indirect relationship. It'll also be, you can see it named an inversely proportional. Those are the same thing. That's the relationship between pressure and volume. Temperature, we'll call T, and the temperature of the gas and the pressure are directly related. The number of molecules of gas, we'll call that N, and the pressure are also directly related. Again, make sure that you go to the video that's already on YouTube to get more details on each of these 3. But I wanted to at least lay out the relationships. We're going to cover most of them in the gas laws that we're going to cover right now. First gas law is Boyle's law. And his deals with pressure and volume. And Boyle's law just says that volume is inversely proportional to pressure at a constant temperature. So the last part is key. If we keep everything else constant, the temperature, the amount of gas, then the volume and the pressure are inversely proportional. So high pressure, low volume. Low pressure, high volume. The equation that we use for that is P1V1 equals P2V2. And what we mean by that is if we have the initial conditions of the gas, when you multiply the pressure and the volume, it should equal the same thing as multiplying the final conditions of the gas, the pressure times the volume. Anytime you see the subscript of 1, we're talking initial conditions. Subscript of 2, final conditions, or what you've changed it to. I'll pause here for a second. If you have any questions, you can let me know. Let you catch up with your notes if you need to. The next thing we're going to do is a sample Boyle's Law problem. So as usual, the problem has a title, right? Boyle's Law problem. So you already know what it's going to be. is the only thing that makes sense. But when you're out there trying to do your exam, you're not going to have that privilege. You're also not going to have that privilege on your homework. So you need to recognize how to solve these problems. And just like with the stoichiometry problems in Chapter 9, or even the mole concept questions in Chapter 8, identifying the problem type is really key to solving the problem. If you don't know what problem type you have, you don't know which gas law to use to solve it. A 7-liter sample of methane gas exerts a pressure of 1,550 millimeters of mercury. What is the final pressure if the volume changes to 3.50 liters? Always pay attention to the numbers. They may not always be relevant, but it's a good place to start. We've got a 7-liter sample with a pressure of 1,550 millimeters of mercury. The question is asking about the final pressure, and the volume changes to 3.50 liters. Based on our context clues, we need to figure out whether each of these numbers is associated with initial conditions or final conditions. The first number that we encounter is 7 liters. Liters is a volume, so it's going to have a V. The first sentence of the problem usually tells you what the initial conditions are, so it's a pretty safe bet that this is the initial volume of the gas. We're told that it exerts a pressure of 1,550 millimeters of mercury. Pressure, we use a P, and this is associated with that 7-liter sample, so it's the initial pressure of the gas. We're asked for the final pressure, which is P2, so we'll put a question mark there. And we're told the volume changes to 3.50 liters. That means we're looking at the final volume being 3.50 liters. What I just did there is going to be very important for you to do when you're solving these problems. You have to assign variables, and then the next part we're going to do is figure out which gas law makes the most sense. Now, we've only gone over one, so there's only one answer so far. But by the end of Chapter 10, we'll have 5 gas laws. Well, 6 really. So there's several to choose from. Whenever you have pressures and volumes, and that's it, you have to use Boyle's law. Boyle's law, P1 V1 is equal to P2 V2. What we're solving for here is the final pressure, which is P2. To isolate that, we have to divide both sides by V2. Whenever you're rearranging your gas laws, you want to group together your pressures, your volumes, your temperatures. That way the math works out nicely, and so does the units. It makes a lot more sense because you can see which unit you need to use to report your final answer in. Now we just have to substitute in the numbers that we have from the problem. make sure that you write the right numbers. I know it sounds silly maybe, but writing in 3.5 liters instead of 7 liters for V1 will cause you to get the wrong answer. So take your time here. And see, I just wrote 7 liters because I was just saying 7 liters. You don't start with liters, you start with pressure. The liters will cancel themselves out. The only unit left is millimeters of mercury. And that's good because we're looking for pressure. I would highly recommend using parentheses here just to make sure that you get the ratio here of the volumes and you're multiplying that by the pressure. When you do this math, your calculator is going to tell you that. But this only has 2 sig figs. We need 3 sig figs. The way to get 3 sig figs is by using scientific notation. That's something that you should watch for, particularly when you're doing your homework, because you don't want to lose points for that. Questions about Boyle's law? Then we'll move on to the next gas law. It's Charles's law. Charles's law looks at the relationship between volume and temperature. The volume of a gas is directly proportional to the temperature in Kelvin. Kelvin is key here. We talked about the different temperature scales way back in the beginning. Here we are again. For gas laws, the only temperature scale that you can use with them is Kelvin. You may be given degrees Celsius or even degrees Fahrenheit, but you cannot use that in a gas law. You must convert Celsius or Fahrenheit temperatures to Kelvin. If you do not convert, you will not get the right answer. This is Charles's law. V1 over T1 is equal to V2 over T2. So these two ratios are equal to each other. As this equation stands, not exactly helpful. You need to cross multiply first. So you multiply V1 times T2 and V2 times T1. From here, you can solve for whichever variable you need. But don't forget to cross multiply first. Otherwise, you might get a little bit lost. I'm going to pause here for a second just to make sure everybody's kind of caught up. And then I'll move on to show you an example of a Charles Law problem. I see a question. So are you saying, can you just start here for Charles's law? Yeah. So what I give you on the equation sheet is going to be this. You need to know that you need to cross multiply and solve for your unknown. So I prefer to rearrange the equation with just the variables and then plug in the numbers. If you feel more comfortable to do just plug in the numbers and then rearrange the numbers, that's totally fine. I recommend doing the variables first just because the less you have to move around the numbers, then the less opportunities you have to write in the wrong number. But whatever works for you, works for you. So don't let me tell you how to do your equations, right? I am merely here to give you suggestions that I have found work. So, we've got a helium balloon. It's got a volume of 132 liters, and it's cooled from 45 degrees Celsius to 25 degrees Celsius. What is the final volume at constant pressure? Let's write out what variables we have, and that will show us which gas law we need. 132 liter helium balloon. That sounds like an initial condition to me, and it's a volume. It's cooled from 45 degrees Celsius. So that must be our initial temperature. It's cooled down to 25 degrees Celsius. That must be our final temperature. And we're asked what the final volume is. Whenever you have temperatures and volumes as given information, you have to use Charles's law. So Charles's law is this. We said cross multiply first. And then you can solve for whichever variable you need. In this case, we need the final volume, which is V2. To isolate that, you divide by T1. That's the equation that we need to use. Then we substitute in the numbers. V1 132 liters. T2, uh-oh, we've got Celsius. We've got to do some converting. To get from Celsius to Kelvin, you add 273. So T1, 45 degrees Celsius, (318 Kelvin). 25 degrees Celsius is 298. You can either convert your temperatures right away as you're writing out your initial information from the problem and figuring out which gas law you need, or you can do it after. Doesn't matter as long as you do it before you start punching in numbers into your calculator. So I always like to double check and make sure that I put everything in right. So T2 is 298 Kelvin. T1 is 318 Kelvin. Great. Before you touch your calculator, here's another trick that you can do. Make sure that you know whether or not you should have an increase or a decrease in your final volume or pressure or what have you. You can't do that for all of the gas laws that we cover, but you can for these simple ones. Volume and temperature are directly related, which means whatever you do to the volume, you do to the temperature. In this case, we went from 45 degrees Celsius down to 25 degrees. That's a decrease in temperature. If we have a decrease in temperature, and we know that the volume has to do the same thing, then we would also expect for the volume to decrease as well. So our answer should be less than 132 liters. Does that logic make sense there? Okay. So when you put this into your calculator, you get there's a bunch more numbers than that, but I'll leave it there. First thing we want to do before we even worry about sig figs is make sure that our result is what we expect. We said the volume would decrease, and 123 point something is less than 132. So that's good. Now we just need to report the right number of sig figs, which we should use 3 here, which I know we're looking at the temperature, there's only 2. But in the Kelvin temperature that we actually used, there are 3 sig figs here. That is a sample Charles's Law problem. Any questions here? All right. Next gas law, Gay-Lussac's law. This one is on pressure and temperature. The pressure of a gas is directly proportional to the temperature in Kelvin. Gay-Lussac's law looks very similar to Charles's law. You'll want to cross multiply first for this one as well. And then you can solve for whichever variable you need to, or just substituting your numbers and do it that way. So Charles's law and Gay-Lussac's law, very similar. You treat them similarly. I'll pause here for a little bit, and then I'll move on to the sample problem, which the problems that I'm doing here are different from the sample problems that I do in the video. So if you need to watch more, you can look at that pre-recorded video and you'll see some different examples. I also go a little bit more into detail and kind of take my time, whereas in class, we don't always have that opportunity. Here we go. We've got a steel container of nitrous oxide at 10.4 atmospheres is heated from -5 to 15 degrees Celsius. What is the final pressure at constant volume? Always start with writing out what you have and assigning variables. That will make the gas law that you need to use very clear. We've got a pressure, which seems like it's an initial pressure. And we know temperatures, starting with -5, and that's our initial temperature, and rising to 15 degrees Celsius. The question is asking for the final pressure. Whenever you're given information is just pressures and temperatures, you're going to use Gay-Lussac's law. And you'll be provided with all of these equations, the gas law equations, but they will not be labeled. So what you'll see is what I just wrote. P1 over T1 is equal to P2 over T2. But it's not going to say Gay-Lussac's law. It's also not going to tell you, hey, make sure that you have Kelvin in there first. It's just going to be the equation. We cross multiply. We're looking for the final pressure. I always like to group my temperatures and my pressures and all that stuff because it makes all the unit analysis much easier. We're starting with a pressure of 10.4 atmospheres, and we're multiplying that by the ratio of T2 to T1. We don't have Kelvin here. We have Celsius. So you have to add 273. Now we can substitute those into our equation. T2 is 288 Kelvin. T1, 268. The units cancel. We know that we're getting atmospheres. Before we touch the calculator, let's make sure that we know which way we expect our pressure to go, increase or decrease. We started with -5 degrees Celsius. We heated up this container to 15 degrees Celsius. That's an increase in temperature. Pressure is directly related to temperature. So if the temperature increases, will the pressure increase or decrease? That's right. The pressure is going to increase too. So when we do this problem, we expect that the pressure should be greater than 10.4. When you work out the math, you get 11.2 atmospheres, and that is more than 10.4, which is what we started with. Questions here? Do you feel like the gas laws so far are simpler than the stoichiometry problems we were doing in Chapter 9? Everyone was like, yes, yes, yes. Okay. So hopefully this will give you a little bit of relief to know that the hardest part is done. We reached the mountaintop. Now we're kind of coming down a little bit, and with something a little bit easier. Now, we'll warn you, we can combine gas laws, not these, but we can combine one gas law with stoichiometry. So they will be grouped together. But I promise you, I will show you how to do that. That'll be next week. So stay tuned. We'll go through the combined gas law, and then we will take a little lay of the land and see if we want to just keep pressing through or if we want to take a little break. But let's do the combined gas law first. Think about that. So we can combine all three gas laws that we just covered. Boyle's law, which was pressure and volume. Charles's law, volume and temperature. Gay-Lussac's law, pressure and temperature. Into the combined gas law. This is for when you have three variables. So the only thing that we aren't changing is the amount of gas. Now I'll show you how we do this one too. So let's say we want to solve for T2. We still need to cross multiply first. So you get P1 V1 T2 is equal to P2 V2, T1. Now, since we're solving for T2, we need to isolate it, which means dividing by P1, V1. The way that I like to write this, I pull the temperature out, I group the pressures together, and the volumes together. That way I can see, okay, my pressure units cancel out, my volume units cancel out. The reason why this is important is because you could get a problem where you have volume 1 in liters and volume 2 is in milliliters, or pressure 1 is in atmospheres and pressure 2 is in torr. So this helps you to make sure that everything lines up, you've got all the right units, and everything's happy. When you're filling in these equations, write in the units. Don't just write the numbers, even if it's on scratch paper that no one else will ever see. Write it all out because it will help you catch mistakes. Now let's try one. We've got a 10-liter sample of carbon dioxide gas. It's at 300 Kelvin and 1 atmosphere. The new volume is 6 liters at 350 Kelvin. What is the new pressure? We'll do what we always do. Write out each given piece of information and assign a variable. The first sentence talks about the initial conditions of the gas. Liters, that's always a volume, so that's V1. Kelvin is a temperature, and that's T1. Atmospheres, that's a pressure, P1. We've got a new volume, so that must be V2. And we're saying that that volume is what it is at our new temperature, 350 Kelvin. What's the new pressure? Whole lot more variables this time. If you're given information is pressure, volume, and temperature, you're going to use the combined gas law. That's what you'll be given on the exam. You need to know how to rearrange it. We're looking for P2. We're going to do just like we did before, isolate it. Divide by V2 times T1. I pull out the pressure. And then I've got V1 over V2 and T2 over T1. Really crucial that you make sure that those subscripts for the initial versus final are clear. Then we put in all of our numbers. V1, 10 liters. V2, 6 liters. T2, 350 Kelvin. T1, 300 Kelvin. You do all the math, and you get 1.94 atmospheres. Now, this is the correct answer. That's what the pressure would be. But the question is asking for the new pressure in millimeters of mercury. So if I put 1.94 into mastering chemistry, it would be wrong. So I need to take this number and convert. So you take that 1.94 and then you have to multiply by 760. So make sure that when you're doing these problems, you pay attention to the units that are being asked for. Because if you don't convert properly, you'll get it wrong, even if you understand the concept. And I think sometimes that's even more frustrating when you're like, but I know this, I understand this, why is this wrong? And it's a small detail, like it's the wrong unit. So make sure that you check for that always. Questions here? So as always, we're at a crossroads. Should we continue or should we take a break? Let me know how you're feeling. Y'all always say keep going, but I always give the opportunity for y'all to change your mind. I understand though, because if we can get done earlier, then that's more time that you have back in your day. Oh, that was all that I had. So we have another question. So there's more to chapter 10 than just this. I wasn't sure how long we would take on the homework. The more that we cover this week, the less we have to cover next week. And the more time that we can either spend on the final, or you can have to do whatever it is you'd like to do. We have another hour that we could continue on. Or you can have that hour now. Which one would you prefer? Okay. Then what we'll do is we'll keep going until about 10:15. And then I won't necessarily, I may try to come back to a reminder slide because we're not going to finish everything, I don't think, in 45 minutes. If we do, I'll be impressed. And then it'll be up to y'all if y'all want to have class next week or not. So if we finish it, then next week could either be a free week, it could be office hours, it could be whatever y'all want it to be. I'm flexible. 8 a.m. class is rough. So last week of classes next week. Y'all might need the extra time. So we'll do quick reminders now and then keep moving forward. So your Chapter 9, Mastering Chemistry, is due this coming Sunday, the 25th. Remember to send me a course message if you want some redo opportunities for some of the questions that you exhausted all of your chances for because you're struggling. Chapter 10 homework is due Sunday, May 2nd. And then your take-home final is due Monday, May 3rd by the end of the day, 11:59 p.m. So I will be posting this week a final exam review. And next week, I will post the actual final exam so that you've got plenty of time to do it. All right. So we'll keep pushing forward. Dalton's law of partial pressures. I kind of don't consider this one a gas law, even though it is. It's so simple that in my brain it doesn't register as a gas law. So, Dalton's law of partial pressures pretty much says the total pressure of a mixture of gases is equal to the sum of the individual pressures of each gas. So let's put that into context. I, for one, would never go scuba diving, but some people like to do that. I'm fine with going to the aquarium and looking at things on TV and on YouTube, okay? I don't have to swim with the fishes. Let them swim with themselves, okay? But if you do go scuba diving, you need some oxygen. Sometimes that oxygen comes in the form of what's called a trimix, where you've got oxygen gas, nitrogen gas, and a little bit of helium. If you have all of those things into one tank, then you've got 3 different partial pressures. And the total pressure, which I usually will do P sub T, would be equal to the pressure from the oxygen plus the pressure of the nitrogen gas plus the pressure from the helium. So that's all we're saying here. The trick is, with these problems, make sure that all of your pressures are in the same units. You'll also want to make sure that you're answering the question in the right unit as well. So whatever unit that is, all your partial pressures should be in that unit. So if you need to answer in atmospheres, make sure all your partial pressures are in atmospheres before you start adding. So here's a sample problem. We've got a mixture of noble gases. It's got helium, neon, argon, and krypton. Very exclusive bunch. We've got all the partial pressures listed here. I'm not going to read them off. I'm just going to highlight them. We have to figure out the total pressure of the sample. Now I've thrown in one little wrench. Everything is in millimeters of mercury, except for the partial pressure of krypton. That's in atmospheres. Now in this question, I didn't specify what unit you should report your answer in. So if this were a question on Mastering Chemistry, you could report any unit, millimeters of mercury or atmospheres. But it makes the most sense to convert the partial pressure that's in atmospheres to millimeters of mercury and then add everything together. And that's what we're going to do. So the first step, convert atmospheres to millimeters of mercury. And to do that, you need to know that 1 atmosphere is equal to 760 millimeters of mercury. And again, you'll have that information. I'm not going to ask you to memorize that. That's just cruel. So our partial pressure for krypton is 174.8 millimeters of mercury. Now, I didn't do any rounding here because that's not our final answer. The second part is what matters the most. You have to sum all of the partial pressures and make sure they're in the same units. So we did that by converting atmospheres to millimeters of mercury. Now we can just take all of them and add them together. When you add all those things together and you take into account sig figs, you get 503 millimeters of mercury. The other thing I want to caution you against, or remind you of, is that let's say you didn't have to do a conversion and you just had everything in millimeters of mercury and you add them up. Don't forget about the rules for adding and subtracting when it comes to partial pressures. So refresh yourself on addition and subtraction sig fig rules. So these partial pressure problems are not difficult, but there are a couple of areas where you can get snagged, and it's frustrating more than anything else because it's such a simple concept. Everybody good so far? All right. I'm trying to give you all of the things I know that you might see on the homework and on the exam. I never want there to be big surprises. So we're going to combine some concepts now and talk about collecting a gas over water. Sometimes you're doing a reaction, like let's say you put zinc metal in sulfuric acid, like shown to the right. You're going to produce hydrogen gas. This is a single replacement reaction. So you're booting out the hydrogen. It's leaving in the form of hydrogen gas. You're making zinc sulfate solution. All the hydrogen gas has to go somewhere, and you can capture it. But when that hydrogen gas bubbles up through and gets captured in here, there's also going to be some water vapor. Every liquid at every given temperature, there's some kind of vapor pressure. And all that means is that some of the molecules on the surface of the liquid have enough energy to free themselves and become vapor. The amount of vapor is dependent on the temperature. So when you collect a gas over water in this method, what you're really collecting is called wet gas, because it also contains water vapor. We can still figure out how much of the gas we're interested in we actually collected, because there's this table. And this table tells you the amount of vapor pressure of water for every temperature going from 5 degrees Celsius up to 100 degrees Celsius, which is boiling, in 5-degree increments. So you can kind of envision this as having kind of a divider. And whatever temperature you're working with, you look it up on the chart so that you know how much vapor pressure is attributed to the water, and you can figure out how much is from your gas. You do not need to memorize this table. The information you need will be provided for you, either in the form of this table or within the problem itself. So here's a sample. A sample of hydrogen gas was collected over 40 degrees C water. The atmospheric pressure is 755 millimeters of mercury. What is the pressure exerted by the hydrogen gas in the cylinder? Whenever you see that something is collected over water, you should automatically be thinking that you need to figure out how much of that is attributed to water vapor. Then we're told the atmospheric pressure is 755 millimeters of mercury. And we need to figure out the pressure exerted by the hydrogen gas. This is actually a Dalton's Law question. Because the atmospheric pressure is our total pressure. And because of Dalton's law of partial pressures, we know that the total pressure has to be equal to the water vapor plus the pressure from the hydrogen. We can look up the partial pressure from the water. 40 degrees. I gave you the partial chart. Here you go. So that's in millimeters of mercury. Again, watch your units with the gases. That's always the trickiest part, making sure you have the right units. But our total pressure is in millimeters of mercury. The partial pressure of the water is also in millimeters of mercury. So that should work out nicely. So we can go ahead and solve for the partial pressure of hydrogen. We have to isolate that partial pressure on one side. And then we can substitute in what we know. So with sig figs, you get 700 millimeters of mercury. Notice how I put a decimal point there? That's because we need 3 sig figs. So that decimal point shows that all three of those digits are significant. The other way to do that would be to simply write scientific notation. So that's another Dalton's law of partial pressures question, wrapped up with the concept of collecting gas over water. Questions? Or are we good to keep going? Alrighty. So this slide goes over the kinetic molecular theory of gases. I'm not going to bore any of you by reading it because you're more than capable of reading. You will need to understand, kind of what this is and kind of be able to answer a question of, okay, which one of these is not a part of the kinetic molecular theory of gases, or which one is. That's really about it. But the nuts and bolts of it is gases move around in random straight lines. They move fast. They don't attract one another. They also don't repel one another. So all the energy that they have, we say they keep, even after they strike each other or the wall. And their energy is proportional to the Kelvin temperature. So that's the kinetic molecular theory of gases in a nutshell. Make sure that you know all these different points and that you can answer that kind of a multiple choice question about which one is or is not a part of this theory. This is the last gas law that we're going to cover, and this is the ideal gas law. I should note here, again, there are a couple of other things that I'm leaving out, but we are covering all of the gas laws. I'm just not going into major detail about each one. I just wanted to give you some more practice problems and things that you can draw from when you're doing your homework. So the ideal gas law is what we use when we need to have information about pressure, volume, the number of moles, which is molecules, and the temperature. Now, I didn't say anything about this R. We didn't say anything about R. R is a constant that's derived from the conditions of STP, the standard temperature and pressure, with 1 mole of gas. If you have all of those conditions, then this is the constant that you come up with, that you calculate. 0.0821 liter atmospheres per mole Kelvin. So you may see it written like that, or you may see it written like that, with moles to the -1, Kelvin to the -1. It's just because that's the units that you need for everything to kind of work out in terms of the units in the math with the ideal gas law. Don't worry yourself with it too much. We're going to do a couple of these types of problems, and then that's going to be it for chapter 10. So y'all are going to get off with a lot more time on your hands, and we can figure out what to do with next week. So we'll do the sample problem, just a straight up ideal gas law problem. How many moles of neon gas occupy 5.75 liters at STP? We defined STP in chapter 8 when we were talking about molar volume. Standard temperature and pressure. The standard temperature is 273 Kelvin, which is 0 degrees Celsius. And the pressure is 1 atmosphere. The ideal gas law takes into account the number of moles. So anytime that you see a gas law question that's asking about moles, that means you need to use the ideal gas law. We rearrange it to solve for N, which is moles. Our variables, we've got 5.75 liters, which is our volume. Our temperature, standard temperature, is 273 Kelvin. The pressure, 1 atmosphere. And the R value that we use in this class is 0.0821 liter atmospheres per mole Kelvin. There are other R values that use different pressures. So if you look that up on the internet, you would find it. However, we don't really go over that in this class, so don't worry about it. Substitute everything in that you know. We've got 1 atmosphere, our volume, that R value, and the temperature. When you do the math, you should get 0.257 moles of neon. So it's just figuring out what all your variables are, assigning those, rearrange, and then plug and chug, which is what they used to say in all my math classes. Plug and chug, plug and chug. I hated that, but I used it. So this is as simple as it gets with an ideal gas law problem. Any questions here? Okay. Then we're going to go to mixing both worlds, stoichiometry and the ideal gas law. So I didn't do this example in the pre-recorded video. I wanted to save it for the live lecture. You'll see something like this on your final. So make sure that you understand how we did it. Whoops. Nitrogen gas reacts with hydrogen gas to produce ammonia gas. How many liters of ammonia can be produced at 0.93 atmospheres, 24 degrees Celsius, from a 16-gram sample of nitrogen gas and excess hydrogen gas? Again, we're looking for how many liters of ammonia. So we've got a whole paragraph, and it doesn't really seem like we have enough information to do anything, but we've got more than enough. Whenever you see a question like this, where you're asked about a volume and you're given other information like the pressure and the temperature, that means you have to use the ideal gas law in addition to whatever stoichiometry you need to do. So here are the steps for this. First thing we're going to do is take the grams of nitrogen gas, convert some moles of nitrogen gas and convert that to moles of ammonia. Then we're going to use the moles of ammonia in the ideal gas law. To solve for the volume. So 2 steps here. The first step, to go from grams to moles to moles of ammonia. Here's what we've got to do. To get from grams of nitrogen to moles of nitrogen, we have to use the molar mass. You look at the periodic table, you look up nitrogen. You multiply that by 2 because the formula for nitrogen gas is N2. Nitrogen is about 14.01, so that means its molar mass for the gas is 28.02, thereabout. To go from moles of nitrogen gas to moles of ammonia, we have to use a mole ratio. And this, just like all our other ones, is going to be in the form of B over A. The nitrogen gas is our A, and our B is the ammonia. So when we write that mole ratio, it'll be the number of moles of ammonia from the chemical equation over the number of moles of nitrogen from the chemical equation. We use the molar mass, 1 mole on top, grams on the bottom. Mole ratio, we're putting B, which is our ammonia, on top. You look at the chemical equation, there's a 2 in front of it. So you write 2 moles of ammonia on the top. You look at nitrogen, there's no coefficient in front, so that's just 1 mole. We get to moles of nitrogen gas, moles of ammonia. In your calculator, 16 divided by 28.02, you multiply that by 2. That math, you should get 1.14 moles of ammonia. Now for part 2. The ideal gas law. We're looking for V this time. Divide both sides by P. Now let's make sure that we know our variables. N is what we solved for. That's the number of moles of ammonia that we'll make. The temperature is 24 degrees Celsius, which you need to add 273 to get the temperature in Kelvin. The pressure, we're told, is 0.93 atmospheres. If this was given to you in anything other than atmospheres, you need to convert to atmospheres. So if I gave you millimeters of mercury, you'd have to convert to atmospheres first, and then use the ideal gas law with the ideal gas law constant, which is 0.0821 liter atmospheres per mole Kelvin. You'll be provided with the gas law constant. You don't have to memorize it. So when you put all that stuff into your calculator, and with sig figs, you get 30 liters. And I use that decimal point because we need to have the right number of sig figs. We need 2. Less concerned about the sig figs, much more concerned that you understand how to do this type of problem. This is as complicated as it will get from me with regards to gas laws. And this kind of knocks out 2 types of problems: stoichiometry from Chapter 9 and ideal gas law from Chapter 10. I'll make sure that one of these is on the exam review that I post so that you can have some practice. Let me know if you have any questions, comments, or concerns. Alrighty. So just remember, so we talked about the Chapter 9 Mastering Chemistry that's due on Sunday. Your Chapter 10 is due the Sunday after that, which is May 2nd. And then your final, which is take home, is due May 3rd. I'll have a review posted for the final this week. I'll post your actual final exam next week so that you can have time to do it. I will also post a survey on Blackboard, and I want you to answer and let me know if you want to have office hours, like drop in office hours for an hour, let's say during our class time next week, if you don't want class, or if you just want to say have an hour of exam review. I'll put some options out there. Make sure that you choose the one that you want, and whichever one gets the most votes wins. So I'll have that survey up probably until Friday, just so that it gives me enough time to prepare for whatever option you guys choose. So I'm not going to hold you to anything, but does anybody have a preference? What you think might be more helpful? Office hours, final exam review, some combination? I have a feeling that it might be, I have a feeling that it might be kind of a combination of things. So what we may do is work out something where, okay, the first hour is this, the next hour is that, just to make sure that we get everybody what they need. So I'll put options up there. I'll send out an announcement when the survey is live. But that's all that I have for you. If you have any other questions, now is a good time. Otherwise, you're free to go.